executive and advisor with over 30 years of experience leading businesses and in the delivery of major infrastructure projects. He's from J-Power, and he has held a variety of positions, including Regional Director for Asia and Group Manager of Innovation and Digital for a 10,000 strong global professional services company. He has lived in Australia, Asia, UK, all over. As you can see, he's now the director of JPLP, the Australian subsidiary of J-Power, which is, to those who are working in the hydrogen industry or the energy economy would know that this is one of Japan's largest utility company. And Jeremy's talk today is actually on Australia's first and only and actively running hydrogen supply chain project, which is the Hydrogen Energy Supply Chain Consortia, which is based out in Melbourne. So with that, without further ado, maybe I'll pass it on to you, Jeremy.
Thank you very much, Raman, and thank you everyone else for joining in and allocating some time this morning. It looks like I'm going to have to share my screen again, so let me just give me one moment. Put that on presentation mode. Okay, hopefully we can see that. I think we're set to go. Okay, well, thank you very much again for your time. You know, the clean energy transition, clean hydrogen, net zero targets, this is all the topic at the moment. So it's a really great industry to be involved in, and it's an important industry for training up our future leaders and future skilled workers who are going to deliver all this. I was saying just before this talk, I went to a presentation last night from Net Zero Australia, talking about what Australia would need to do to hit net zero. They were saying we need 1.2 million workers in the northern part of Australia to deliver all the work needed to deliver our net zero target. So very exciting times. Today, though, we're going to talk about our project. It's the Hydrogen Energy Supply Chain Project. The first stage is a pilot. I'll go into a bit more detail about it later. But our aim is to create carbon neutral hydrogen through the extraction from Latrobe Valley coal and biomass, a mix with carbon capture, utilisation and storage. So just a little bit about J-Power, if you're not familiar. So J-Power is one of Japan's largest energy utility companies, established 60, 70 years ago, 25 gigawatts of generation capacity. So to give you some sense of scale, that's around about 2.5 times that of AGL. We're already 50% renewable in Japan, and that renewable energy comes from things such as geothermal, pumped hydro, and a bit of solar. And we want to do a lot more, particularly offshore wind. But so we're already 50% renewable. We have our own net zero target by 2050 as well. And J-Power invests a whole range of clean energy technologies around the world, everything from wind and biomass, solar, pumped hydro. For example, the Kidston pumped hydro project in Queensland, you may be familiar with that project. It's the first pumped hydro project in Australia for 40 years. We're the major shareholders in that project. And also we're very much interested in hydrogen, which is why we land ourselves on this particular project. So this project is all about reducing CO2 emissions. It's a CO2 reduction focus. That's the aim. We wouldn't be talking about this project if we weren't talking about CO2 reduction. That's what we need to do. And we see this project is another tool in the toolbox to bring down our atmospheric CO2. But why? What's the background? Why are we doing this apart from the CO2 reduction? Well, Japan imports around about 90% of their energy as fossil fuel. So 90% of Japan's energy is imported through oil, gas, and coal. And they have their own net zero targets by 2050. So their aim is, how do they change their energy mix to be net zero? Yes, they can do a little bit more on renewables. So offshore wind is a particular focus at the moment. Nuclear, they were going to go ramp up their nuclear capabilities, but we had the 2011 Fukushima nuclear accident, which put Japan in a moment of reflection about how best to handle going forward their nuclear capabilities. And you will notice just of last week, they're now going to speed up reopening and constructing more nuclear power plants in Japan. And hydrogen became their focus. So in actual fact, hydrogen was the first, so Japan was the first country which had a hydrogen strategy. Australia followed in 2019, but in 2017, Japan had a hydrogen strategy, and this project was set up to prove that we could have a complete hydrogen supply chain. So producing it, liquefying it, shipping it, and unloading and successfully and safely using it in Japan. Just as a very quick background about hydrogen. So hydrogen is a very versatile fuel. It can be both has storage capabilities, storage of energy, but it also burns clean. So with the hydrogen combined with oxygen, we get only H2O plus the energy we need. So therefore, from the Australian context, it's going to be a great energy exporter. Top left-hand corner, it can be used for heat. It can be used in transportation, such as fuel cell electric vehicles, particularly on the heavy vehicles, buses and trucks, where the payload of a battery would be too big. The hydrogen would be a great opportunity for there, and chemical feedstocks. And right now we produce around 70 million tonnes of hydrogen is produced around the world, mainly to make ammonia, but this is unabated. So in other words, around about 800 million tonnes of CO2 is released to the atmosphere right now in producing hydrogen. So we can see that there's been the Hydrogen Council and other organisations have looked at how the hydrogen global demand may increase over the years. So right now, as I mentioned, 70 million tonnes of hydrogen. They're looking at about an 8-time increase to 2050. We don't know if that's should be 6 or 10 or 12, but it's a very major increase in the hydrogen demand, but that would have to be clean or low emissions hydrogen. So that's the opportunity in front of us. And if we were to do that, you can see the effects it has on the global economy. So our energy demand would be made up of 20% hydrogen, roughly, about a 20% reduction in the CO2 emissions, which is about 6 gigatons, 2.5 trillion sales, and hundreds of thousands of jobs. So a great opportunity, a great industry to be involved in. Let's talk a bit about our project. So it was first imagined, so Japan had their 2011 hydrogen strategy, but they needed to find a way to bring this clean, low emissions hydrogen into the country. So this project was set up to prove the liquid hydrogen supply chain. And there was 2 phases. The first was the pilot and then the full commercial scale. So we're going to talk initially about the pilot, and the pilot is a demonstration project to prove up the various elements, various infrastructure of the complete supply chain, mixing Latrobe Valley coal with biomass to produce this hydrogen, 99.999% pure hydrogen, which is what is needed for liquefaction. The commercial phase will come later once we've secured off-takers. Our vision is something like 225,000 tonnes per year of hydrogen. And that's where we're heading, and that's what we're working on at the moment. So if we look at the complete supply chain, you'll read in the press and you'll read lots and have presentations about people proposing to produce hydrogen. Very important. But we need to prove up every element of it to make this a workable solution for the countries like Japan or South Korea or Singapore, which are very heavily dependent upon importing their energy. So on the left-hand side, we've got the gasification of coal and biomass and the gas refining, the purity part of producing that pure hydrogen. So that's what we have in Latrobe Valley. For the pilot, we will transport that compressed pure hydrogen to the port of Hastings, where Australia's first liquefaction facility has been built. We then load it on an existing terminal, a wharf there, and load it onto the world's first liquid hydrogen carrier, the Suiso Frontier, the hydrogen frontier. And then we unload it in the port of Kobe. For the pilot project, there is no carbon capture and storage, so we release the CO2. It's about 500 cars worth of CO2, so a relatively small amount, but we have purchased carbon credits for that. In the full commercial scale, we'll have a full CCS system, which I'll talk about a bit later. So this is a $500 million pilot, so very expensive, and therefore has taken many organisations coming together with a shared vision. So my company, J-Power, there's Kawasaki Heavy Industries, Marubeni, Sumitomo, Iwatani, Shell, ENEOS, AGL. And we have been very grateful to receive support from the Victorian government of $50 million, the Australian government $50 million, and the remaining $400 million from the Japanese government, as well as some of those organisations you see, particularly the ones on the left-hand side. So a lot of hard work, a lot of courage to put this project together many, many years ago, well before people were talking about hydrogen. So the vision of those leaders is incredible, and I certainly tip my hat to those leaders who put this together. So if you're familiar with hydrogen, you'd be aware of typically the three sorts of hydrogen which are currently produced. One is deemed grey hydrogen, which is a fossil fuel without carbon capture and storage, which is how most of the 70 million tonnes of hydrogen is currently produced. Then there's the blue hydrogen, which is a fossil fuel with carbon capture and storage. And then there's the renewable hydrogen or green hydrogen, which is using renewable energy through an electrolyzer to split water. So if you look at blue and green, people often say, well, if you can make green hydrogen, why do you bother making blue hydrogen? And we offer these three main reasons why. The first of all, this is an emissions reduction project, and we need to start reducing CO2 now. We cannot keep waiting for some perceived perfect solution. We've got to start doing it now, and this provides that opportunity. We've also talked about the scale of the challenge in front of us, and the third reason is the economics. So if you look at the carbon reduction opportunities, so at a commercial scale, 225,000 tonnes of hydrogen per year, we estimate we would save around about 1.8 million tonnes of CO2 going into the atmosphere, which is roughly the equivalent of the emissions of some 350,000 cars. So a very positive contribution in providing a low carbon solution of hydrogen, but also reducing the atmospheric CO2. The second reason I provided is scale. And so Dr. Alan Finkel often talks about this example just to get us thinking about the scale of the challenge and opportunity which is in front of us. So if we were to produce as much hydrogen as currently the energy content is produced in 70 million tonnes of gas. So we export around about 70 million tonnes of liquid LNG per year. That equates to about 30 million tonnes of hydrogen, given the difference in energy density. Now, to produce that hydrogen through renewables, we would need 8 times Australia's 2018 energy production capability. So 8 times that to produce that 30 million tonnes of hydrogen. So not that it's not achievable, but it's a massive scale, and it simply takes time to ramp up to that level. Hence, use all the tools we have in the toolbox to keep lowering our emissions and build up a skills base and to start this industry. And the third reason I spoke about was economics, the cost of production. So most research indicates that our form of hydrogen production, gasification with CCS, is around about a half to a third of the cost of renewable hydrogen production. Of course, that is site specific, but that gives a sense of scale, and price is important. We believe ultimately the customers or the off-takers or the end users will want to know what is the carbon intensity of the hydrogen and what is the equivalent cost. And I often talk about how we currently now go into a petrol station and can choose between 98, 95 and 91 petrol. Each has a different price point. So as a customer, you would choose what you need or what you're comfortable with, both in terms of the quality, 98, 95, 91, or the price point. And we think with Australia's Guarantee of Origin scheme, which will validate the carbon intensity of the hydrogen, will provide that number, the carbon intensity for the hydrogen, and also the equivalent price point which comes with it. So the customers will end up deciding as a tradable energy source around the world. So for those who are unfamiliar where we are, so we're in Victoria, in the Gippsland, southeast of Melbourne, where we have the gas, the hydrogen production, and the export terminal and the liquefaction facility. Now, here are some pictures. So this project, so we have built and have operated the pilot project. So during COVID, very challenging times, we actually built and started operating this facility. So an incredible job by all of our project partners and the teams who are working on this. Very challenging times, both with human resource challenges, but also the supply chains and getting all the equipment needed to put this together. So here we have the gasification and refining facility at Latrobe Valley, where I'm currently at the moment. So the gasification is around, it's high temperature and pressure, so around about 1500 degrees centigrade and 2.5 megapascals. And we crush the coal, dewater it, add oxygen, and through that we generate hydrogen. We then do a water shift reactor where we refine that syngas, which is produced to get more hydrogen and also pure CO2. So therefore, we have that opportunity to have high hydrogen content and a stream of pure CO2. And that pure CO2 is easily captured because it's a byproduct. We don't have to actually go and find it as you would with the thermal power station. So you've got the CO2, and in a commercial scale, we will use that where possible in making other products such as methanol or urea and fertilizers, but also in the food and beverage business, and safely store the rest in underground disused or depleted oil and gas reservoirs. I'll talk about that a bit later. At the Port of Hastings, we have Australia's first liquefaction facility. And here we drop the temperature of the gaseous hydrogen down to minus 253 degrees centigrade. So pretty cold. And that reduces the volume down to 1/800th, enabling it to be more easily and efficiently transported either domestically or over the waters. And as a reference point, LNG is minus 161 degrees. So you've got minus 161 on LNG to minus 253 with hydrogen. So that gives you a sense of the scale of what's needed. As part of our project, we have built and operated the world's first hydrogen carrier ship, the Suiso Frontier. So that arrived in our port. It's made several trips, but arrived in our port in February of this year, successfully loaded the hydrogen, transported that liquid hydrogen to the port of Kobe, successfully unloaded. And that hydrogen has been used in a variety of applications over in Japan, and the ship has made several trips since. So that's something which has never been done before, and again, needed to prove up and get all the maritime approvals for safety and so on, but also to understand things like boil off, what's the boil off rate and what needs to be done in the future for a larger commercial scale operation. The port of Kobe here in Japan, next to the airport or near the airport, we have the receiving terminal, again, built and operating, and that is enabling us to learn what needs to occur at the arrival point, and also the off-takers coming and taking that, and the distribution systems needed to take that liquid hydrogen to the end users. In terms of the project pipeline, so that green bubble which came out there, so that's the pilot operation. So we've been operating for more than a year, and this year we completed our pilot operations in actual fact. So a few months ago, we wrapped up all the testing, all our activities as part of the pilot. So right now we're actually analysing all the data to enable future works, more cost-effective, safer than what we've done before, in readiness for a commercial scale. At the same time, as you can imagine, we're looking and talking with many, many off-takers, because this project will only stack up. In fact, any hydrogen production project will only stack up if we've got guaranteed off-takers. How much hydrogen do they want? How long do they want it for? How many years what's the price? And when would they like to start receiving the hydrogen? So with that information, we can start to put forward a bankable document and go and secure financing from ourselves as equity, but also as debt as well. At the moment, we're talking about having a commercial phase operation put together by the end of the decade. But again, it may be a bit earlier, maybe a bit later. It's going to depend on these off-takers. So talk is good, but we need the actual commitment of off-takers to be able to get these projects off the ground. In a commercial vision, it looks fairly similar to what you see here, but I'll just highlight a couple of differences. So on the left-hand side, we've got the coal and biomass gasification and refining. Just so you're aware, we have a 170 megawatt gasification and refining facility in Japan, much, much larger than what we have here. And that is producing hydrogen. We have a carbon capture system as part of that process as well. So a very large demonstration project. And that will end up being the train size we use. So when we go into commercial projects, we'll have that size train operating. So multiple trains if we want more and more hydrogen. So Osaki Coolgen, 170 megawatts, that's the basis of our commercial operation. I mentioned carbon capture there. So in our solution at commercial scale, we will need a carbon storage solution. So you may be familiar with a couple of projects, which I'll talk about the next slide, in Gippsland, very close by to us, using depleted oil and gas reservoirs very close as a safe and secure way of storing the CO2. In terms of taking the hydrogen from our plant to a port, rather than trucking it, we'll have a hydrogen pipeline. So that would be a much more cost-effective way and safer way of doing that. And of course, we'll have much larger ships taking our hydrogen. So carbon capture and storage. So this is often discussed concept. And I just really wanted initially to provide some facts because there's lots of information out there. Some of it I think is misleading, but these are the facts and everyone can make up their own mind about it. Over the last 45 years, there's been 27 of these facilities built, storing around about 40 million tonnes of CO2 per year. To my understanding, there's been no leakage in any of these storage facilities. There's around about 135 more of these projects in various stages of development around the world, from the US, Canada, UK, Europe, China, Japan, Southeast Asia, Australia. Because IEA and IPCC also recognise to hit our carbon neutrality targets, we need to do multiple things at the same time. And carbon capture and storage is a proven technology which will be needed to hard to abate industries, plus as we get the transition into even more cleaner, lower emissions fuels. So that's the background. And for our project, we actually have two opportunities. The first is the CarbonNet project, which has been in development for around about 10 years with the support of the Australian and Victorian government. So they want to use depleted oil and gas reservoirs in Bass Strait, about 120 kilometres from where we are, so nice and close. They've been in development for 10 years and they've been working in parallel with us. In other words, we both require each other. So one has not gone in front of the other in terms of project development. They've done their testing. They've test injected water to mimic CO2 going into the system. They're looking at their monitoring systems, and we would be one of their early customers and foundation customers. You may have heard recently that ESSO is also looking to have a carbon storage system in Bass Strait as well to initially handle their own CO2, but potentially could take on our CO2 as well. So they've got 50 years, 5 decades of knowledge of the reservoirs, the natural reservoirs out in Bass Strait. Many of those reservoirs are now depleted and have, frankly, recently been storing gas, LNG, as a way of buffering their supply and demand. So very adequate and very suitable for storing CO2. So we're confident and comfortable that this is a good solution for our project. We're not necessarily supporting it around the world, but for this project, it makes sense. It's close, pure stream of CO2, very good storage capability. Around about 31 gigatons, it's estimated, of storage capacity in Bass Strait, which is almost the world's emissions in any given year. So to wrap up, I'd like to highlight that this project is about emissions reduction. We firmly believe that's what's needed. With the mixture of biomass coming into our gasification process, we can be carbon neutral, even carbon negative. That CO2 allocated from the biomass can be used as carbon neutral CO2 to make other chemicals, such as methanol, ammonia, then back into urea, add the ammonia with CO2 to make urea, fish proteins, many great opportunities to come and to drive a circular economy in this particular process. Jobs, we estimate about 1,000 jobs a year would be created over the life of the project. So, for example, if it's 30 years, 30,000 jobs. So for the Latrobe Valley and Gippsland, very important. Jobs is very important because the power stations are closing. There's no turning back. These power stations are closing. The next to close is Yallourn in 2028. So there needs to be an orderly transition of industry and workers here in the valley. So a very important part of that. And the third part, why we think it's great for Victoria and Australia, is export opportunities. It'll be a value-added product being exported rather than the raw material, such as raw coal or LNG. We are exporting a refined, clean energy to the rest of the world. So great opportunities there for export income.